Hello, welcome you all again to this online NPTEL course on fundamentals of composites and cellular materials. So far we have discussed about the basics of composite materials, and then we discussed about different fibers, their synthesis techniques. In today's class, I would like to introduce a new topic, which is basically metal matrix composites. So, we will talk about their basic concepts, and then we will talk about how we can synthesize metal matrix composites. So, the plan here is to talk about metal matrix composites, the basic concepts, and then how do we classify MMCs, and then we will start talking about synthesis of MMCs. So, yes, metal matrix composites, we all know that it is a composite material where the matrix is metal, and then reinforcements could be different kind of either ceramic materials or any other different kind of fibers or particles. Okay. Now, the first question I would like to ask here is that why do we need MMC, and we have discussed that also in the other classes, that metals or alloys, they have very good ductility and they have fairly high strength also, but then in certain cases you need to increase the strength, or basically to improve the modulus and strength both. You want to have high temperature strength, high temperature properties. So, that is why metal matrix is synthesized, reinforced with high strength particles and fibers. Okay. Now, if you look at the classification of MMCs based on reinforcement, obviously we have three different classes. One is particle reinforced MMCs, and then short fiber or whisker reinforced MMCs, and continuous fiber. Okay. So, basically these two are fibers, one is short fiber, other one is continuous fiber, and then the other class is the particular reinforced composites. So, you can see here how it looks like, the schematic. This is a particle reinforced MMC, and then this is whisker or short fiber reinforced composite, and then ultimately you have this one is the continuous fiber reinforced composite. And obviously you would like to know that what kind of fibers are used here. So, you can see here particle, short fiber, continuous, all are being used. Particles aspect ratio obviously is close to 1, and then you as you move from short fiber to continuous fiber, aspect ratio keeps on increasing. And examples of these different particles or fibers are SiC, Al2O3, boron nitride, B4C, so on and so forth. Okay. Along with these three classes, we should not forget another class of reinforcement is in situ reinforcement. That means, in the melt itself, melt of the metal or alloy itself, a second phase gets introduced or second phase gets formed, and that acts as reinforcement. And the advantage of having this kind of in situ reinforcement is that the interfacial strength is extremely high or very good. Okay. The weightability is very good, and that ultimately leads to better load transfer from the matrix to reinforcement. Okay. So, now let us look at certain examples of MMCs. You can see here this one is Al2O3 fiber reinforced magnesium alloy composite. The magnesium matrix here has been reinforced with Al2O3 fiber. Here you can see again this is an aluminum alloy matrix, but in this case this is not fiber, but particles. These are actually short fibers, as you can see here, sorry, SiC fibers, actually as you can see here. Okay. I think this one is labeling has been done wrongly. This is SiC particle, not fiber. Yes, these are all SiC particles have been used in reinforcing the aluminum alloy matrix. Okay. And you can see compared to the other metals or alloys, obviously when you talk about composites of metal matrix, they have higher tensile strength and higher modulus. And the comparison, you can see titanium alloy steel, okay, they have higher modulus, you can see here, obviously then aluminum, if you compare with aluminum, they obviously have higher modulus and strength, but then if you have the same aluminum alloy, okay, but reinforced with SiC particles, that means you are keeping the weight again lower, okay, but then you are achieving a higher strength and a higher modulus. That means the specific strength of the material increases as you reinforce with particles or fibers. I already discussed that MMCs will be having higher elastic modulus and strength, lower coefficient of thermal expansion. Okay. The lower coefficient of thermal expansion is because of the second phase, and then superior elevated temperature properties, again because of the reinforcement, and higher temperature properties means obviously creep resistance and rupture strength increases. So, now let us talk about how can we synthesize metal matrix composites, and the basic techniques are centered around liquid state processing, because metals are easy to melt, metals and alloys they are easy to melt. So, mostly people rely on liquid state processing, and you can see here a series of different liquid state processing starting from compocasting to bottom pouring to melt infiltration, reactive liquid metal infiltration, spray forming, centrifugal casting. There are a lot of different techniques. Similarly, in solid state processing we have diffusion bonding, power metallurgy, friction stir processing, and I would like to discuss these techniques one by one to give you some idea of how MMC can be synthesized by these different techniques. So, we will start with liquid state processing, and the first one, the first method in liquid state processing which I want to discuss is called compocasting or rheocasting or melt stirring or dual can process. Compocasting, why compocasting? Compocasting means casting of composite material. Why are you calling it rheocasting? Rheology is involved here, that means the viscosity of melt is extremely important in this process, that is why it is called rheocasting. Similarly, the melt is stirred here, that is why it is also called melt stirring, and the commercial name of this process is dual can process, by which aluminum SiC composite was synthesized firstly. So, that the commercial name is dual can process. So, what is done here is that the schematic shows nicely the whole process. So, you have the ceramic particles which needs to be used as reinforcement, and then the ingots are here of the alloy. So, first a special treatment is done. What do you mean by special treatment? Special treatment of the ceramic particles. Okay. Now, the ceramic particles, as you can see here, okay, ultimately needs to go into the metal matrix, and it should have good wettability. So, the ceramic particles are treated, maybe some coating of other product, so that the wettability improves. Okay. And once the wettability improves, also sometimes the ceramic particles are coated with certain material, so that this reinforcement does not react with the interface. That means also to restrict unwanted interfacial reaction. That is the treatment is done, and another thing is done also, the ceramic particles are heated a little bit, so that it gets mixed well. And so, heating means basically it will not be having any absorbed gases on the ceramic particles, so that the mixing will be easier. Okay. So, ultimately these ingots are molten, and then these ceramic particles are added. Okay. But is there anything special here done? Obviously, the melt is continuously stirred, so that the ceramic particles gets distributed evenly inside the matrix. Okay. Now, why this is required? Why ultimately the stirring is required? That is because to avoid any macro segregation of the ceramic particles. As we all understand, ceramic particles, they have low density, right. So, then when it is when you put it in a liquid metal matrix, liquid metal or alloy, it tries to float above the surface. Okay. or when you are stirring it also, it makes a vortex, and then in the vortex there could be some macro segregation. So, obviously, the stirring has to be optimized, so that you get a nice and homogeneous mixing of the reinforcement particles in the melt. Okay. And then after the melt is completely homogenized, then you can go for the secondary process like extrusion, making the billets, then making this again this ingot or this kind of rolling blanks. Okay. Now, that is what actually has been discussed here, that ceramic particles and ingot grade aluminum are mixed and melted, and the ceramic particles are given a proprietary treatment, that means to improve wettability and to restrict any kind of unwanted interfacial reaction, and then the melt is stirred just above the liquidus temperature, generally between 600 to 700 degrees Celsius, and this is where I am talking about aluminum alloy. Okay. And then the melt, once the melt is nicely mixed or homogenized, then it ultimately billet or ingot or rolling blanks are made. If you look closely in the stirring process, so what you see here, that this is the melt zone or the chamber, and this chamber there are actually these heating elements which is heating the metal matrix higher temperature than their melting point. Okay. So, some amount of superheat is added here, and then the ceramic particles are added and it is stirred vigorously. Okay. So, now why this stirring is needed and advantages? Yes, homogeneous mixing of reinforcement particles, and as I was mentioning earlier, because of density difference there could be macro segregation. To avoid this macro segregation, stirring has to be optimized. Also, the stirring improves the wettability. Now, once the wettability means what? Wettability means the wettability between the reinforcement and the matrix, molten matrix. If the wettability is better, then there will be better interfacial adhesion, and if the interfacial adhesion is better, as we all know, there will be good load transfer from matrix to reinforcement, efficient load transfer from matrix to reinforcement. Now, how could we optimize this homogeneous mixing and wettability? We are talking about homogeneous mixing and wettability. So, there are a few factors we need to take into account. Okay. First of all, what kind of particles are these, fibers or particles? If particles, then what is the shape and size? Okay. For example, let me just quickly try to draw it. Okay. So, we could be having particles, or we could be having this kind of fibers. Okay. And if we have particles, we could have large particles and small particles, larger particles and smaller particles. Now, if the particle size is smaller, okay, what is the change happens? The specific surface area actually increases as you decrease the particle size, as you all understand. If we keep the morphology same, means let us say spherical particles, and if we decrease the particle size or decrease the diameter, then specific surface area increases. As soon as the specific surface area increases, what happens with the viscosity, melt viscosity? The melt viscosity actually goes down. The melt viscosity that actually goes down if the specific surface area increases, because then you have higher amount of surface area which needs to be weighted by the molten metal. So, obviously, the viscosity goes down. Okay. And again, how can you control this case? Let us say you want to have, so first thing is that, yes, you have to take care that the viscosity does not go down too much or does not reduce too much, then the stirring would be difficult. At the same time, in some cases you would like to have smaller particles. So, then how can you actually retain the higher viscosity? By supplying higher amount of superheat, or basically to increase the melt temperature above its melting point. Okay. And that is how you can control the wettability. You can clearly see in this equation that let me change it to laser pointer. You can see here that as the volume fraction increases, the viscosity of the melt increases. Okay. this is the viscosity of the melt without any reinforcement, and as you keep on adding the reinforcement, or if you keep on increasing the volume fraction, the viscosity also of the melt also increases. So, we have to take care of certain factors. One is the size of the particle. Okay. So, if I just try to write it down, one is the diameter of the particles. Okay. One is the diameter of the particle, okay, large, small. Okay. Also, we have to take care of the volume fraction, how much we are adding, okay, and these two basically are the primary factors which can affect the viscosity, and we can improve the viscosity or increase the viscosity by adding the superheat. Okay. So, that is how we can control the wettability. Okay. So, ultimately it has to be optimized. Now, so you can see here that even the densities of the melt and the reinforcement particles are different. This way, by optimizing the different process parameters, we can have a homogeneous mixing of reinforcement in the matrix. But then what is the problem in this method? Yes, problem is that it is a high temperature process and you are keeping the reinforcement for a long time inside this melt. That actually leads to interfacial reaction in some cases. Okay. And if there is interfacial reaction, there could be unwanted interfacial product formation that has to be avoided some way. Okay. Okay. So, that is the basics of compocasting or rheocasting. Now, let me quickly talk about certain examples. So, you can see here in this particular table there are three different kind of alloys have been reinforced, all aluminum alloys, but the alloy composition or the alloying elements are different. These two are wrought, and then this one is actually a cast product, and obviously the alloying elements are different. So, you can see here with increase in Al2O3 amount, obviously the yield strength increases, modulus increases, and elongation decreases. No rocket science in that. Okay. So, in all cases you can see as you increase the amount of Al2O3, modulus and strength increases and the elongation has to go down. Okay. Now, if you compare with these two, 6061 and 2014, obviously 2014 shows higher strength, you can see here clearly, and that is because 2014 contains copper. The main or primary alloying element in 2000 series is copper, and that actually leads to formation of, giving of this what do you call it, these are edge hardenable alloys. So, that improves the strength. Okay. In case of 6061, these are basically silicon and magnesium alloy, magnesium are the alloying elements. So, again these are used in automobile industries. This has fairly good strength, but not as high as the 2000 series. So, now let us show another new technique, which is basically a modification of the star casting where bottom pouring is done. Okay. So, here basically the pouring of melt into the mold happens from its bottom. So, you can see here this is the stirrer and this is where the melt is being used actually is kept. Okay. So, the melting furnace is this one, and then the reinforcements are actually added through this particular setup. Okay. Reinforcements has to be preheated. So, let us quickly see what are the steps. Initially the furnace temperature is raised above the liquidus temperature, okay, and talking about aluminum matrix, so 720 degrees Celsius, and then cooling down, so that you make a slurry or semi solid state, and then preheating of the reinforcement is very much important in terms of proper mixing, as I was mentioning earlier. If you preheat, then it will be not be having any absorbed gas. Also because of higher temperature of the particles, when it goes into the melt, it does not go through any kind of residual stress or less amount of residual stress, that does not crack the reinforcement particles. Okay. And then ultimately the similar stirring is done, optimized stirring, and ultimately there will be a bottom pouring facility here through which the melt will be poured out. Okay. So, it is basically a modification of the compocasting method, that is method 2. Method 3, okay. Now the point here is we have to improve. If you remember, what was the problem with compo casting or star casting is that the residence time in the melt of the particles is quite high. That leads to interfacial reaction in some cases, and you want to avoid that. So what can be done? How can you improve that? Melt yield filtration is one of the technique of that. And then we have different kind of melt yield filtration technique. One of that is gas pressure infiltration. So what is done in gas pressure infiltration? A melt is prepared of the matrix material, okay, and then by gas pressure this melt is pushed upward direction. What do you have here? You have a preform here. What is preform? Let me talk about that first and then I will come back here. So preform is basically loosely bound particles or fibers which will be having enough amount of porosity, okay. So it is basically a green compacted particles or fibers which will be having enough amount of porosity, and the idea is to infiltrate this porosity with the molten metal. So there are different techniques by which this preform, so you can see here this is the preform, okay, and this preform is what, as I mentioned earlier, this is basically loosely bound, not completely compacted, loosely bound second phase, that is particle or reinforcement, particle or fiber which you want to use as reinforcement. So it will be having good amount of porosity, certain amount of porosity, and that has to be calculated how much porosity you leave, because ultimately those porosities will be filled with metal matrix and that will be the volume fraction of the metal matrix. So there are different ways. One is press forming. In the press forming, what is done? A slurry is made. Now what is this slurry? Basically there will be a solvent. In that solvent these fibers or the particles will be added, okay, and along with that some amount of binder, some amount of wetting agent will be added, okay. So you have this slurry which contains the solvent. In the solvent you add the fiber or the particles, also you add some binders, and you also there will be addition of some amount of wetting agents, okay, and then this slurry will be actually poured into this kind of mold. And what is happening with this mold? This mold contains this perforations or holes, okay, and there will be a piston will be there also, and this piston will also be having certain amount of perforations and holes. So now as you press this liquid down, the slurry down, the solvent, in this case the water, comes out and you get the fiber preform, and this process is called press forming, because you are forming the preform by application of pressure. Similarly, a method is there which is called suction forming. In suction forming, the preform is made by suction. So again you can see here there will be this kind of cavities, and these cavities are also again having certain amount of porosities, okay. So through this pore this slurry would go in, okay, and then as the suctioning is done through these perforations here, okay, so then the solvent goes out through this pipe and ultimately we get a preform again. So this preform is made by suction process, that is why it is called suction forming. So the ultimate idea here, either by suction forming or by press forming, is to make a preform, and then this preform is kept here. So now I think it is clear to all of you what is a preform, okay. And now as I mentioned few minutes back that by application of inert gas pressure, this molten metal is pushed through a riser into the form. So that is how the infiltration takes place, okay. So in this case, what are the advantages? Clearly the residence time is less, shorter residence times, that means more reactive material can be used compared to compo casting, or in other way interfacial reaction would be, the chance of interfacial reaction would be less, okay. And you are applying a pressure, argon gas pressure, that means the amount of porosity will be less, because this preform is infiltrated with a pressurized melt. So, the amount of porosity would be less obviously, and as it is a preform, that means the the fibers are already homogeneously distributed, okay, and that homogeneously distributed fibers is now actually infiltrated with the melt. So, that is why we have all these advantages. Okay. Now, obviously, the question would come in our mind that can we do better, can we go for a little bit better process. Okay. Obviously, you can do better, we can go for again infiltration process, but we can change the infiltration process a little bit, so that again the residence time goes down. So, for that the process which is used is called squeeze casting. From the name only you can understand, in this case no argon gas pressure is used, but ram is used here. So, you can see here that the melt has been poured and then a ram comes down which pushes the liquid in few seconds inside the preform. Okay. So, the whole process takes place in a few minutes, few seconds. Okay. That the ram moves slowly and pushes the liquid into the preform. So, what are the advantages here? Obviously, residence time is quite low. So, yes, porosity free matrix, because you are applying a very high pressure even compared to gas pressure infiltration. Wettability is better again because of the higher pressure, okay, and again because of higher pressure less reaction time. Okay. That means, because in this case the pressure infiltration is done by a ram, okay, rather than an argon gas pressure. So, the pressure is quite high, and that leads to porosity free matrix, better wettability, and reaction time is also less. Another very important point here is to note is that as the solidification process takes place quite fast, so there is a fair chance of achieving fine grain in the microstructure. Let me just say it once more, is that the whole process, as you can see here, the whole process takes place in a less time, and then the whole melt is surrounded by heavy blocks of metals. So, the heat removal is quite efficient here, quite fast here, and that leads to fine grained structure. So, in melt infiltration we have two techniques. One is, as I mentioned earlier, air pressure infiltration or inert gas pressure infiltration, and then we have squeeze casting. Both are superior than compo casting in terms of better wettability, less reaction product formation and all those things. And if you compare gas pressure infiltration and squeeze casting is better again because of all these advantages. So, example has been shown here earlier also. You can see here the example here, this is alumina fiber which is used to reinforce aluminum matrix, has been made by squeeze casting. Similarly, another example has been shown here where ultimately you can see this is a aluminum matrix which is reinforced with SiC particles. Okay. Very high amount of SiC particles can be used actually here, 50%. Okay. And again squeeze casting can be again they have different variations. It could be direct squeeze casting, it could be indirect squeeze casting. The difference between direct and indirect is that in indirect there will be a gating system through which multiple preforms could be infiltrated. In direct squeeze casting it goes directly, okay, in one preform. So, now what is the advantage of, or what are the advantages of indirect squeeze casting? In indirect squeeze casting, the residue, because in the melt will be, there will be some amount of oxide formation in the melt. Whatever you do, it is difficult to avoid oxide formation in the melt, and that residue actually will be remaining in the gating system here in case of indirect squeeze casting. Okay. Also, as the flow is getting divided into multiple channels, the turbulence of the melt would be less, and lower the turbulence of the melt, the chance of gas entrapment is also less. Okay. I hope you understand this point, that because of multiple channels, here it is a single channel, here there are multiple channels through which the liquid is flowing. So, the pressure is getting distributed and it is going through multiple channels. So, ultimately the turbulence in the melt would be less, and once the turbulence is less, then obviously the gas entrapment, or ultimately these gas entrapped gases will be acting as porous, will be leading to porosities. So, amount of porosities will also be less in case of indirect squeeze casting. Okay. So, with that information, today's class I would like to conclude. So, in today's class we talked about metal matrix composites. They show very high elastic modulus and strength compared to their metal or alloy counterpart. Coefficient of thermal expansion is low. It shows improved creep resistance and rupture strength, that means high temperature properties are better. And then we started talking about the synthesis of metal matrix composite, and in today's class we talked about compo casting, where the melt is stirred and then pre-treated ceramic reinforcements are added, and we talked about melt infiltration, where the sole purpose or sole aim is to improve wettability, reduce residence time at high temperature and restrict interfacial reaction. Okay. So, dear students, with that I would like to conclude today's class. In the next class I would again continue on metal matrix composites only. We will talk about some more synthesis techniques. We will also introduce about solid state processing, and then we will talk about applications, and if time permits we will talk about case study as well. So, this is the references, you obviously need to consult these references for better understanding. With that I would like to conclude here today. Thank you all.